Hello, my name is Bill Robbins. In this video module I'm going to discuss MOSFETs that are designed for power electronic applications. More specifically, I'm going to talk about the following topics. First, we'll talk about the construction of a power MOSFET, what its vertical cross-section looks like. We'll then talk about the IV characteristics, then the physical operation of the MOSFET, then the switching characteristics of MOSFETs, factors that limit the operating specifications of the MOSFET, and finally a new variation of the MOSFET, the so-called cool MOS or superjunction MOSFET. Going back to the first topic, the next slide shows the vertical construction of a MOSFET, so-called vertically diffused power MOSFET or VDMOS. You'll notice that the current is oriented or will flow in the vertical direction from the drain down at the bottom surface, upwards through the drift region, bending over at the interface, and finally going out the source diffusion on the top surface where there is metallization to contact to the outside world. There are thousands of unit cells kinetically in parallel. This diagram only shows two of them, one here and one here. The width of the gate is shown. Each unit cell has a fairly small gate width, but with thousands connected electrically in parallel, the effective gate width of the power MOSFET is very, very large. In fact, the gate width to channel length ratio is very large, sometimes on the order of 100,000 or more, compared to the much smaller values one sees for signal level MOSFETs. If I go on to the next slide, we get a blown-up view of this vertical cross-section where I can describe some of the specific aspects in somewhat more detail. Here we show, as I said, the vertical cross-section. The current flow path is shown, and there are two unit cells. The channel area of each unit cell is this area here and corresponding area over here. The length of the channel is described here in the drawing, and it typically is well under a micron. Because of the basic construction, there are some parasitic elements that we have to deal with. Most importantly, we have a parasitic bipolar junction transistor. The N- drift region forms the collector of the parasitic transistor. The p-type body region is the base of the transistor, and the source diffusion is the emitter. The basic problem is we do not have access from the outside world to the base of this parasitic transistor, and so we have no way of controlling what its state is. And if for some reason it gets turned on, we have no way of turning it off, and that could severely compromise the operation of a converter in which this MOSFET is being used, or perhaps even destroy the MOSFET. So one of the features of modern power MOSFETs is we have a body to source short. In other words, the source metallization not only contacts the N+ diffusion, it's extended out in this area right here so that we have the source metallization contacting the body, and thus we have a so-called body to source short. The consequence of this is, from a circuit viewpoint, the base emitter junction of this parasitic transistor is shorted out, and thus it's going to be much more difficult for it to ever turn on. As a consequence of the base to source short, we still have the collector base junction, and that means we now have an anti-parallel diode that comes along with each unit cell, and so correspondingly the overall MOSFET has an integral anti-parallel diode between the drain and the source. Some manufacturers control the properties of this integral parallel diode so that it can be used in converter circuits. However, most manufacturers do not give much data on the diode, and the implication being they don't have it well controlled. And so in those MOSFETs, one should not count on using the integral diode as part of your basic circuit operation. The other feature I would call your attention to is the gate metallization, which is shown here just above the oxide layer. That gate metallization normally only extends over the channel area, but in a power MOSFET, we extend it completely over the drift region as it comes up from the bottom surface to the top surface, so that this plate, if we want to call it that, or gate metallization, functions as a field plate. for the same reason that we need field plates in PN junction diodes. Without the field plate action of that gate conductor, the reverse bias junction between the drift region and the body would have a very sharp radius of curvature where the boundary between the two regions bends from being parallel to the top and bottom surface to being vertical. And so in this region right here, in the reverse bias operation, we could have a very sharp radius of curvature which could otherwise compromise our breakdown voltage if we didn't have the field plate action. Finally, the thickness of the drift region from here to here is set by the required breakdown voltage that we want to have for this particular device, and the doping level in the drift region is set also by the breakdown voltage considerations. There are other geometries that are being used for MOSFETs. The next slide shows two of them. The upper picture is of a trench gate MOSFET, where we actually etch a trench into the top surface of the silicon and partially fill it with oxide, then put a gate conductor in, and then cover that gate conductor and surround it by more oxide. In this case, the current flow now is entirely vertical because the channel region is formed right here and right here. And because of this construction, this device has lower on-state resistance than a comparable VD MOS, comparable meaning same current carrying capability and same breakdown voltage. The lower picture is of the first practical power MOSFET, the so-called V-groove MOSFET. It also has a trench etched in it, but it's at about 45 degrees. And because of the limitations of the technology, this tends to have higher on-state resistance than either the trench gate or the vertically diffused MOS. And so modern devices are not made using this particular type of technology. Moving on to the next topic, the IV characteristic of a MOSFET is shown in the next slide. Here in the upper left, we see a typical picture of a MOSFET characteristic, and if one didn't look carefully at the numerical scales on the vertical and horizontal axis, one would assume that this is probably a signal level MOSFET because they look identical. But when one looks at the numerical scales where we have tens of amps perhaps for drain current and hundreds of volts for the drain to source voltage, we realize this is for a power MOSFET. We have basically the same regions of operation. If the gate to source voltage is less than the threshold voltage, the device is in cutoff and we have zero drain current. If we have a very large gate to source voltage, we'll be operating over here in the ohmic or so-called triode region, and at intermediate values where the current characteristics are flat independent of the drain to source voltage, we're in the active region. If we have too large of a drain to source voltage, then we could go into avalanche breakdown, and that's shown here by the vertical rise of current at the BVDSS rating. BVDSS stands for breakdown voltage between drain and source when the gate is shorted to the source. To the right, we have the characteristic of the transfer curve, that is drain current as a function of gate to source voltage at some constant drain to source voltage when we're in the active region. At low gate to source voltages, just a little bit above the threshold voltage where the drain current isn't too large yet, we would expect to see the typical square law relationship between gate to source voltage and drain current. But at higher gate to source voltages, where we're now conducting larger drain currents, this relationship becomes linear. And so the drain current at most of the range of allowable drain current is linearly proportional to the gate to source voltage, and we'll discuss that a little bit later. The circuit symbols that we use for power MOSFETs are the same as for signal level MOSFETs. The body region electrode is shown shorted to the drain to the source, as we indicated earlier when we were talking about the vertical cross section. This is your N-channel MOSFET symbol. Here's the P-channel. In most applications, we're going to use N-channel MOSFETs because the on-state resistance is lower due to the higher mobility of electrons compared to holes. In some specialized circumstances, for example, if we need level shifting or some other requirement, we may use P-channel MOSFETs. The next topic is the physical operation of the MOSFET. When someone who is unfamiliar with MOSFETs but in general familiar with p-n junction diodes looks at a MOSFET cross-section for the first time, he's puzzled by how it can possibly operate, because no matter which way you bias the drain to source terminals, either drain positive, source negative, or vice versa, there's a p-n junction that's going to be reverse biased, or at least apparently so. If the drain is positive with respect to the source, it's the drain body p-n junction that is reverse biased. And yet, by the application of a gate to source voltage, we can somehow cause current to flow. And we need to talk about what that mechanism is. From a naive viewpoint, one knows that in order to have current go from drain to source, we have to somehow make the body region look like it's N-type, at least a portion of it. So we have a complete path from drain to source through the body region that looks like N-type material. Well, that's what the function of the gate is. If I apply a fairly small voltage to the gate, I've labeled it VGG1, we begin to put positive charge on the upper plate. That means on the lower side of the oxide, at the oxide p-type body interface, we're going to have some negative charge to compensate for that positive charge. Well, we can obtain that negative charge by creating a depletion layer and causing the depletion layer boundary to move downward, and thus exposing some of the ionized acceptor impurities which carry negative charge. If we increase the gate to source voltage, the depletion layer will grow more, but it can't grow fast enough in proportion to the increase in the gate to source voltage to provide all the negative charge. We remember that when we were talking about step junctions, the depletion layer boundary increases as the square root of the reverse bias voltage. And so if I double the gate to source voltage, I double the positive charge on the upper plate, but I do not double the thickness of the depletion region. So I have to have some other source of negative charge. Fortunately, there is a large reservoir of electrons that are free to move in the source diffusion. And so the high electric field at the body region oxide interface will attract some of those electrons, and they will be then attracted to the interface between the oxide and the body region. And I show then some of the negative charge being, without being encircled, as the ionized acceptor impurities. The electrons, or the negative symbol with the circle around it, are the free electrons that I've attracted. So now I have a mixture of different types of negative charge. If I increase the gate to source voltage even larger, as I'm indicating in the upper right hand corner, I ultimately are going to attract so many free carriers, free electrons from the source region, that they dominate the electron density at the interface. The free electron density is going to be much larger than the ionized acceptor density. And when we reach a point where the number of free electrons is numerically equal to the acceptor density, we call that an inversion layer. And at that point, the gate to source voltage is equal to what we call the threshold voltage. And as I increase the gate to source voltage larger than the threshold voltage, I begin to increase the thickness of this so-called inversion layer. And so now I have a path for current to flow. I've converted the area just under the oxide in the body region from p-type material to n-type material. And so now I have a conducting path from drain all the way to the source, and so current can flow. The exact voltage at which inversion occurs is a function of several factors, including the type of material that I use for the gate conductor, the doping density, and the body region underneath the gate. If there's any bound impurities in the charge, that will affect it. And most importantly, the oxide capacitance per unit area. It's possible during the manufacture to adjust the threshold voltage by implanting more impurities into the body region right under the oxide, and that is done by ion implantation. Now, so far I've been describing the operation without considering any flow of current. We go to the next slide, we begin to have to take that into account. What I'm showing now is the cross-section of a single unit cell, and I'm now applying a drain to source voltage through a resistor. So now drain current is beginning to flow. Because of the current flow from the drain end toward the source end in this direction parallel to the interface that I've been talking about, I'm going to have a voltage drop along the channel. That voltage drop, if we make the reference for that voltage drop the source, it's smallest as I'm adjacent to the source, and as I move in the positive x direction toward the drain, the channel to source voltage increases. And now it's clear that the total externally applied gate to source voltage is equal to the voltage across the oxide, as I've diagrammed, plus the channel to source voltage at that position x. That means at the drain end, where I have the largest channel to source voltage, I have the smallest voltage developed across the oxide. And so the thickness of the inversion layer, which is governed by the oxide voltage, is going to change. It's going to be thickest at the source end and smallest at the drain end. And it's clear that at some point, if I keep increasing the drain current, I may have at the drain end a vanishingly small thickness for the inversion layer. And that brings up the question, how can current possibly flow if I thin down or even eliminate the inversion layer at the drain end? Well, the next slide discusses that point. If I increase the drain current to such an extent that the channel drop is large enough so that at some finite distance away from the drain, I pinch off the channel or inversion layer so that I don't have any inversion layer at all, I then have a situation where the shaded area, which is the depletion region of the reverse bias body to source junction, is in series with the current path. And so the question is, how can current flow through a depletion layer? Well, the answer is, I have a very high electric field due to that inversion layer. It's in the direction positive on the drain end and negative as I go toward the inversion layer. That electric field is in contact with the inversion layer where there are free electrons, and so that drags free electrons out of the inversion layer, accelerates them across the depletion region, and so we have current flow. This is very reminiscent of the same thing that happens when one has in a PIN diode, when one has reach through, where the depletion region has reached completely through the lightly doped drift region and reached the N-type material. That drags electrons out of there and very high currents can then flow. Well, in our situation, we don't have an infinite source of electrons because the inversion layer, the number density of electrons is much, much less than what it is in the source, and so we have a limited number of electrons available, and the effective resistance of the inversion layer is thus relatively constant, and we have a fairly fixed voltage across it from the end of the inversion layer down to the source diffusion, and so constant voltage divided by a constant resistance means we're going to have a constant current. This is also aided, this constant current is also aided by another phenomenon, which is drift velocity saturation, which is indicated in the next slide. In silicon and most semiconductors, at low applied electric fields, the electron velocity is proportional to the electric field, and the slope of the curve is the mobility. But in silicon, when we reach 10 to 20,000 volts per centimeter, the velocity saturates at a constant value, about 8 times 10 to the 6 volts per centimeter. So we have then, no matter what the electric field is above that 20,000 volts per centimeter, we have a constant drift velocity. And so this mechanism is also part of the explanation of why we have a constant current at a fixed drain to source voltage and fixed gate to source voltage. Another way of looking at this is the mobility is becoming inversely proportional to the electric field as you increase the electric field that is pushing electrons through the channel, and this process is part of the explanation of why at higher drain currents we have a linear relationship between the gate to source voltage and the drain current. The next topic that we have in the outline is the switching speed of MOSFETs. I'm going to use the buck converter shown here in the upper left-hand portion of this slide to describe the switching behavior. So we have a MOSFET that we turn on and off by means of the applied voltage V sub GG in series with a resistance R sub G. We have the freewheeling diode that connects the drain to the DC power supply, and in parallel with that is a constant current source that represents our load current. We're going to be representing the MOSFET by an equivalent circuit. Either in cutoff or the active region, the equivalent circuit is composed of a dependent current source activated by the gate to source voltage. Between the gate and the source, we have a gate to source capacitance. Between the gate and the drain, we have a gate to drain capacitance. For in the active region, we have a positive current, non-zero current being put through the dependent current source. If the gate to source voltage is below threshold, zero current is coming out of the dependent source. When we're in the ohmic region, or the on state, we model the MOSFET as a small resistance between drain and source, the so-called on-state resistance, RDS on, and we still have gate to drain and gate to source capacitances. Now these capacitances have different behavior depending on which capacitance you're talking about. The gate to source capacitance is basically the capacitance due to the gate oxide between the capacitance between the gate and the source and the gate and the adjacent body region, and that capacitance is pretty much independent of applied voltages. There is a small capacitance between the drain and source, which in some applications or analyses one needs to take into account, but we're not going to discuss that in this particular module because for most applications it isn't all that important. Probably the most important capacitance is the gate to drain capacitance. There are two contributions to that capacitance. There is the oxide capacitance, which I'm drawing right now, and then in series with that is the depletion layer capacitance. The oxide capacitance doesn't change with drain to source voltage, but the depletion layer capacitance does, because as I increase the drain to source voltage, I increase the thickness of the depletion region, and thus I lower the gate to drain capacitance across the depletion layer. Here I show on the right hand side a graph of gate to drain capacitance versus drain to source voltage. At low drain to source voltages we have a fairly large value, which I call V sub GD2. At high drain to source voltages a much smaller value. In a lot of power MOSFETs, this variation in capacitance can be more than 10 to 1. And so this has an important effect on what the voltage versus time looks like between drain and source as we turn the MOSFET on and off. If one looks at the spec sheet for a MOSFET and attempts to find on the spec sheet information about these capacitances, one is going to be somewhat puzzled by the fact there is no indication of what the gate to drain and gate to source capacitances are, at least not directly. Instead, what most manufacturers do is measure capacitances in a slightly different way, and those can be related to the gate to source and gate to drain. For example, if we bias the MOSFET in the middle of its active region and then incrementally short the drain to the source, for example by putting a large capacitor across there, and measure the capacitance between gate and source, this is a so-called input capacitance, CISS. And it's clearly in this diagram equal to the gate to source plus the gate to drain capacitance, because that puts those two capacitors in parallel, and the drain to source capacitance is shorted out. Similarly, on the output side, if I incrementally short the gate to the source and measure the output capacitance between drain and source, that capacitance, labeled COSS, is equal to the gate to drain plus the drain to source. Finally, in order to measure the gate to drain capacitance, or so-called reverse transfer or feedback capacitance, we put the device biased in the active region into an AC bridge, as indicated, and by balancing the bridge we can directly measure then what the gate to drain capacitance is. and that's usually specified on a spec sheet as CRSS. Alright, now we get down to the important details, which are, if I turn the MOSFET on and off, what do the waveforms look like? Well, here are the MOSFET base buck converter at turn on. At t is equal to 0, I ramp up the driving voltage from 0 to V sub GG plus in a step function-like manner. However, the gate to source voltage doesn't immediately jump because we're charging up the gate to source terminals through that resistor R sub G. So there's an exponential rise in the gate to source voltage, and until the gate to source voltage reaches the threshold voltage, nothing changes. When we reach the threshold voltage after a so-called turn-on delay time, which one can calculate from this equivalent circuit that I was showing earlier, then the drain current begins to rise. We assume it rises linearly, and we can calculate how long that takes because it's based on how long it takes the gate to source voltage to go from the threshold voltage up to a large enough value to support the current I0, and that corresponding value of gate to source voltage I've labeled VGS I0. And so again, using our equivalent circuit, I could estimate T sub Ri if I know all the capacitance values and the value of Rg and the power supply voltage V sub GG plus. At this point, the gate to source voltage becomes constant, and it's forced to become constant because what is going to happen is we have a constant current going through the MOSFET, and the external circuit will only provide that current. And so at this point, the gate to source voltage remains fixed, and all of the gate current now flows through the gate to drain capacitance toward the positive power supply and then down to ground. And so by this means, we are causing the drain to source voltage to drop down toward 0. Initially, it's going to go with a very fast transient, very steep slope because we have a fairly small value of gate to drain capacitance. At some point, and one would have to look on the spec sheet to find exactly what that drain to source voltage is, at this point, after this time interval t RV1, we have to take into account the fact that that capacitance, gate to drain, has gotten much larger. And so in a two-parameter model, such as I illustrated earlier for the capacitance, we then have to use the gate to drain 1 value, which is much, V gate to drain 2 value, which is much larger, and hence a much shallower slope to the final on-state value of drain to source voltage. During that entire interval until we reach the on-state voltage, we essentially have constant gate to source voltage. After that point, then the gate to source voltage resumes its growth toward V sub GG plus, and the gate current continues its decay down toward 0. Just to reiterate how one can use these equivalent circuits that I was describing earlier, here's a little bit more detailed explanation. During the turn-on delay time, our equivalent circuit is shown here in the upper left. I'm charging up the gate to source and gate to drain capacitances, which are in parallel. And when I reach the threshold voltage, then I have the current beginning to be commutated out of the freewheeling diode and into the MOSFET, and so we're gradually taking the current away and putting it into the MOSFET. And that takes a time interval T sub Ri. Once I've commutated all the current out of the freewheeling diode, now I can begin to reverse bias that diode, and so the drain to source voltage now can begin to drop. And so here on the lower left-hand side, I show the equivalent circuit for the TFV1 interval, where we have a relatively small value of gate to drain capacitance. We're now in the mode where we have a fixed voltage between gate and source, so I don't even bother showing the gate to source capacitance. And that current that is flowing, the gate current, goes entirely into the gate to drain capacitance and then flows to ground through the dependent current source. When I reach a low enough value of drain to source voltage, I still have the same equivalent circuit, but now I have to change the value of the gate to drain capacitance to the larger value C gate to drain 2. In a lot of spec sheets, instead of giving specific capacitance values, they instead show what is called the turn-on gate charge characteristic, and that's shown on the next slide. What it is a plot of the gate to source voltage as a function of a charge that we've put on the gate source terminals. Initially, we start at zero charge, and we are ramping up the gate current and thus the gate to source voltage. And when we put in amount of charge Q on, which is enough to enable us to have the MOSFET handling the entire load current, we have a linear growth in the charge. Then we have the plateau region where we have a constant gate to source voltage, but we're still putting more charge in there because all that charge we're now putting in the second region, which is labeled Q sub P, is the charge that's going on to the gate drain capacitance to lower the voltage from the power supply voltage down to the on-state voltage. And then finally, there is a third contribution of the charge, which is labeled in this diagram Q total 1 minus the sum of the first two charge contributions. That charge is the overdrive, if you like, that we're putting on the gate source terminals to be sure that is deeply into the ohmic region. And it will turn out that the amount of that charge is somewhat dependent on what the drain to ground, what the power supply voltage is. In the right hand side of this slide, just to equate the what's going on, I have the equivalent circuit for the circuit, and I'm showing the gate to source voltage as a function of time, the drain current, and the drain to source voltage. And one can see from particularly the gate to source voltage as a function of time looks almost the same as the charge curve, and in fact one gets from one to the other by converting the time axis into a charge axis, because we can estimate what the currents are that are providing the charge. And the definitions of the various charge contributions are shown here in the lower left hand side. The analysis that I just went through, or this quick overview if you like, assumed that we had a perfect freewheeling diode. If we have a non-ideal freewheeling diode, things change a little bit, and we put extra power dissipation into the MOSFET because of the non-ideal behavior of the diode. The upper curve is a plot of the freewheeling diode current during the MOSFET turn-on, which starts at t is equal to 0. The diode, after the turn-on delay time and then at the start of the current rise time interval. The diode current begins to decrease, and it decreases starting from the value I0 down to 0. That takes the time interval t sub Ri, the current rise time, and corresponding to that, the drain current goes from 0 up to I0. But because this is an imperfect diode, the diode current then goes negative, peaking out at a negative current whose magnitude is a so-called reverse recovery current, and then it goes down to 0. And correspondingly then the MOSFET current has to increase above I0 up to the peak value I0 plus IRR before it decreases down to I0. And the time interval that it adds to the region where we have both large current and large voltage is the reverse recovery time of the diode. Until the reverse recovery current peak is reached, the diode voltage, the MOSFET voltage can't change. It's equal to the power supply voltage. Only after the MOSFET current decreases from the peak value down toward I0 do we have the decay of the drain to source voltage. So clearly we're putting more power into the diode because of the imperfect nature of the freewheeling diode. We extend the time that we have high power dissipation, and we're also increasing the current during that interval above the current I0. I'm not going to discuss in detail the turn-off characteristics because it's just the inverse of the turn-on. We start with a large gate to source voltage, the overdrive value, and at t is equal to 0 we either set the gate drive to 0 or a negative value. At t is equal to 0 then the gate to source voltage begins to decay until it decays down to the value just needed to keep the current at I0. In this interval then we'll have a constant current, and the drain to source voltage during that plateau region first increases slowly and then much faster because of the change in the gate to drain capacitance as a function of the drain to source voltage. When the drain to source voltage reaches the power supply voltage, then the current can drop. And so during the current drop, we have then the continued drop in the gate current and in the gate to source voltage. And one can use the same equivalent circuits to roughly estimate what these turnoff times are. Now there are several factors that we have to take into consideration when we're actually applying a MOSFET in a particular circuit, and these are the subject of what I called operating limitations. Older MOSFETs, particularly the V-groove technology, usually had specifications put on the device by the manufacturer, and in particular one of those was a VDT limit, meaning there was a maximum rate of rise of the drain to source voltage that the MOSFET could tolerate, and this rate of rise then would be when we're going from the on state toward the off state. The problem is illustrated in the figures in the upper part of the slide here. On the left hand side I show the vertical cross section of the MOSFET, and in particular the gate to drain capacitance and a resistance, particularly the resistance of the body region that connects the body region to the source. An equivalent circuit, at least an approximate equivalent circuit of this, is shown. Here's the ideal MOSFET, the parasitic BJT, the gate to drain capacitance, and then that so-called body region spreading resistance that connects the base to the source. If we have very large VDTs between the drain and source, then I'm going to have current coming down the gate source capacitance. And if that current is large enough that I get something like 7/10 of a volt across that body region spreading resistance, I could turn on that parasitic BJT, and that's what we're trying to avoid. And perhaps one of the circuit arrangements where this is most serious is in a half or a full bridge, when we have the lower section of the bridge, the MOSFET perhaps is off, but we have an integral diode carrying current, so that means there is stored charge in the body region. And if then at some particular time we attempt to turn on the upper transistor while maintaining the lower transistor in the off state, what could happen is we would then have a very large increase, very rapid increase in the drain to source voltage across that lower transistor. I could then have displacement current coming down like this through the body region spreading resistance, and I could turn this device on. And what makes it even more serious is I already have the diode biased with stored charge in the base region, so it is much easier to turn it on than if we had no current flowing at all and no stored charge at the instant I tried to turn on the upper transistor. So one has to be quite careful in using particularly older MOSFETs in half bridge and full bridge circuits, and be aware of these VDT limits. Modern power MOSFETs are much more immune to this problem. Going on, there is a maximum gate to source voltage that one can apply, and the manufacturer specifies it usually as V gate to source maximum or some other easy to interpret symbol for the maximum gate to source voltage. If you exceed that voltage, you have the possibility of rupturing the gate oxide because of large electric fields across the oxide. SiO2 typically will begin to rupture between 5 and 10 million volts per centimeter across the oxide. Typically in a power MOSFET, the gate oxide is 1,000 angstroms thick, sometimes somewhat thinner. So if we take 5 million volts per centimeter times 1,000 angstroms, which is 10 to the minus 5 centimeters, we get a maximum gate voltage of 50 volts. Well, no manufacturer is going to give you the full 50 volt rating. He's going to be very conservative and say the maximum voltage might be 20 to 30 volts. So when you're handling MOSFETs, make sure that you are well grounded so that you don't put static charge on the gate just by careless handling and destroying the device. I could tell you stories of how I have in past years been demonstrating MOSFET circuits to undergraduate laboratory classes, and I have ruptured the gate oxide and ruin the diodes. The breakdown voltage is another important rating or limitation, and that is shown in the next slide. Again, the vertical cross-section of the MOSFET, and as you're aware by now, we have to have a field plate action using the overlap of the gate metallization over the drain region as it approaches the oxide interface to prevent a sharp radius of curvature from causing lower breakdown voltages than we had designed for based on a plain parallel depletion layer boundary. The thickness of the drift region, which I'm indicating here, and the doping density N minus is determined by what the breakdown voltage rating for the MOSFET is. And what we want to do is make sure that we use the device wisely and make sure that under all circumstances we don't exceed that breakdown voltage rating. And in particular, if there are inductances in series with the MOSFET that may cause overvoltages, we may have to consider the use of appropriate snubber circuits. The MOSFET on-state losses have several contributions. If we're talking about a low voltage MOSFET, something on the order of 100 volt or at most breakdown voltage, then the contributions to the on-state losses come from all parts of the device. There is the resistance of the source diffusion that I've indicated, the resistance of the channel, so-called accumulation layer resistance, which is where the current is now in the drain region but begin to bend over from being horizontal to the top surface to going vertically. There is the drift region contribution, and finally the drain region contribution. All of these are perhaps equally important at low breakdown voltage ratings. As you increase the breakdown voltage rating of the MOSFET beyond 100 or so volts, then the drift region dominates the on-state resistance. And one can show in a simple calculation that the on-state resistance in silicon MOSFETs at these higher breakdown voltages is proportional to this numerical factor, 3 times 10 to the minus 7 times the square of the breakdown voltage divided by the cross-sectional area of the drift region through which the current is flowing. This on-state resistance increases as temperature increases due to the fact that the mobility of the carriers goes down as we increase the temperature of the silicon. It's possible to put high voltage MOSFETs in parallel and thus come up with a composite device or system that can carry significantly more current. And that's shown in the next slide. The reason that we're able to do this is because of the positive temperature coefficient of the on-state resistance. This gives us a thermal stabilization effect. For example, if the resistance in on-state resistance of Q1 is larger than the on-state resistance of Q2, which I'm just putting in a symbol for now, then more current, and thus there will be higher power dissipation in Q2. But as a consequence of this, the temperature of Q2 will increase, perhaps higher than the temperature of Q1, and thus its on-state resistance will become as large or larger than that of Q1, and so some of the overcurrent that was there temporarily will go back to Q1. And so we have this thermal stabilization, which makes it much easier to consider paralleling MOSFETs. Some bipolar devices have a negative temperature coefficient, which means as one of the devices in parallel gets hotter, it has a better conduction characteristic and takes even more current, and thus hogs most of the current, and that can lead to thermal runaway, a positive feedback situation. The next slide here that I've just brought up is the MOSFET safe operating area. This is sort of a summary of some of these limitations that I've been talking about for the last couple of minutes. It's a plot of the drain current as a function of the drain to source voltage. The maximum drain current, I sub dm, is not a thermal limitation. It's due to a limitation on how much current density you can have either in the thin film metallizations that contact the diffusions or the bonding wires that connect the thin film metallizations to the outside world. If those current densities get too high, we can blow apart the conductors. In other words, they can act as a fuse, and so that's the source of the maximum drain current. The maximum drain to source voltage is the BVDSS, and that's this vertical line that you see on here. The slanted line, about 45-degree orientation, is a thermal limit. If we have very slow switching speeds, or basically if we're operating at almost DC conditions, then we have a fairly limited safe operating area, because what is happening is there's a maximum temperature to which we can subject the interior of the silicon. Typically that maximum junction temperature is on the order of 150 to 175 degrees centigrade. If it gets hotter than that, then you're exceeding the ratings that the manufacturer guarantees, and you're at the very least compromising the reliability of the device quite severely, and you may even lead to failure. So the safe operating area in this condition is this shaded area that I'm indicating here. Any load line within this safe operating area is legitimate. So this would be a safe load line. If we had a load line that was outside of the safe operating area, such as this one or this one, the first one here is too much current flow. This one we exceed the breakdown voltage. And so we want to make sure that our load line stays within the safe operating area. Now fortunately for us, we're not limited in power electronics by the DC condition. We're limited by how fast we can switch. And so what I'm showing here is if you can switch the device on and off progressively faster and faster, here I'm talking about a millisecond, 100 microseconds, less than 10 microseconds, you can approach then a larger safe operating area that's basically square, set by I sub dm horizontally and BVDSS on the vertical side. And so that's why we try to operate these devices as fast as we can in making the transition from being off here to being on here, or going the other way from being on to being off. We want to make the transition through this active region where we have a combination of large voltages and large currents, which means high instantaneous power dissipation. We want to pass through that region as rapidly as possible. The last topic I want to take up in this video is a comparison of the standard vertically diffused MOS MOSFET with the newer geometry, sometimes called cool MOS, sometimes called super junction MOSFETs. The upper picture here shows a cross-sectional view of a conventional vertically oriented MOSFET. The one on the bottom is the cool MOS structure, and the thing that distinguishes it from the standard structure is these very deep p-type diffusions that are connected to the p-type body region. These protrusions, or so-called p-type pillars, almost touch the N+ diffusion down by the drain, and generally the doping in the p-type region here, or the p-type pillar, is identical to that of the doping magnitude in the n-type drift region. And moreover, the width of the p-type pillars and the n-type drift regions are the same, and I've designated that width as B. And the overall vertical dimension of the drift region is designated as W. To understand why the difference, I'm going to discuss the cool MOS operation first in its blocking state. If we apply a drain to source voltage at some very modest voltage, which I've designated here as V1 between the drain and source, the depletion regions between the p-type body and the n-type drift region begin to expand. And they're going to expand equally into the p-type region and the n-type region because of the equal doping densities. Because of the very long vertical dimension, the depletion regions grow horizontally toward each other from each of these junctions, these arrows indicating the general direction of growth of the depletion region. At some relatively modest applied voltage, which I designate as V sub C, these depletion regions meet here in the middle of the drift region channel. And after that, the entire cross-sectional area of the device is depleted. If we use a step junction formalism, we can show that the voltage at which this merging of the depletion regions first occur is given by the formula that I'm showing right here. It's equal to the electronic charge Q times the dimension B squared times the doping density of the drift region divided by 8 times the dielectric constant of the silicon. At the same time, we have to satisfy the equation that the voltage V sub C is equal to B times the maximum electric field in the horizontal direction divided by 4, because the electric field profile at this point is triangular in shape, as we have seen for a standard step junction. V sub C and V sub B are design variables, and we can show that the drift region doping, I'm calling it N sub Cm for N common mode, is given by the formula down here at the bottom, and we can adjust that depending on what the desired V sub C and B are. Going on to the next slide to finish this discussion. For applied voltages larger than V sub C, we begin to have the total electric field rotated from a horizontal position toward more of a vertical position, because now the voltage that's greater than V sub C is being applied across a completely depleted region. The increase in voltage does not have to result in any increase in the space charge because we've completely depleted this. And so we essentially have a uniform insulator, if you like, between the drain and the source. And so now our electric field profile becomes spatially uniform in the vertical direction, with the electric field given by the applied voltage divided by W. The doping level in the N-type drift region can be much greater than that in a conventional vertical diffuse MOS of a similar breakdown voltage capability, and I'll illustrate that in another slide or two. At breakdown, the vertical field is going to equal the breakdown voltage in silicon of 300,000 volts per centimeter, and the voltage at that point, the so-called breakdown voltage, is equal to that breakdown field strength times the thickness of the drift region. In the on-state, we can estimate what the on-state resistance per square is, that is R on times A for the cool MOS. It's going to equal W divided by Q times electron mobility times the doping density in the drift region. Now recall that we've already shown that the doping density is given by this equation, which involves the parameter B. Similarly, breakdown requirements require that the drift region length W be equal to the breakdown voltage divided by the field strength. So if we make those substitutions into the equation for the on-state resistance times its cross-sectional area, we get the following result. And you'll note that that resistance per square is proportional to the dimension B squared and to the desired voltage V sub C at which depletion of the drift region first occurs. Well, we now are in a position where we can compare the on-state resistance per square for both VD MOS and for cool MOS. For vertically diffused MOS, the on-state resistance per square is given by the formula which I have here. I'm not going to derive it, but it can be found in several references, including the textbook that Mohan, Undlin, and Robbins have written. If we use that formula and the formula that we derived for the for the cool MOS and form the ratio, we get the equation that I show right here. And it's best illustrated perhaps by a numerical example, so I will assume a breakdown voltage of 1000 volts, a dimension B equal to 10 microns, and I'll use the standard breakdown field strength of silicon, 300 kilovolts per centimeter, and a voltage V sub C of 30 volts where depletion first occurs in the drift region. This corresponds to a cool MOS drift region doping of about 1.6 times 10 to the 15th per cubic centimeter. And similarly, for a vertically diffused MOSFET, the drift region doping would have to be 3 times 10 to the 14th for a 1000 volt device. That means when we put these numbers in here, the on-state resistance of the cool MOS is about 1/10 that of the equivalent vertically diffused MOS device. Now this is an approximation, but it is reasonably close to what is observed experimentally. Typically, it's argued that it's more like a factor of 1/5 for the ratio rather than the 1/10 that I have here. I've given a reference for a more complete analysis that one can look at for more details about cool MOS. Finally, a few words about the switching behavior of cool MOS. Here I show a MOSFET switching waveform for a clamped inductive load. Cool MOS is generally going to be faster than vertically diffused MOS for similar device ratings, that is, similar voltage and current. The reason being, cool MOS is going to have smaller capacitances, including CISS, CRSS, and COSS. And this is a result of the smaller size of the cool MOS device, because it has a higher drift region doping and thus lower on-state resistance. So for equivalent devices with equivalent on-state resistances, cool MOS is going to be substantially smaller. Another way of putting it is the gate charge required to turn on a cool MOS device is going to be significantly less than that for a vertically diffused MOS. I'm not going to go any further into the details of cool MOS. This is just to give you a very basic idea of what cool MOS is and how it differs both in structure and in performance compared to a vertically diffused MOS. And there are now available cool MOS devices with breakdown voltage ratings as high as about 1200 volts in silicon. Thank you for your attention.